Research on the application of on-board energy storage on an electric locomotive for quarry railway transport. Improving efficiency and reducing harmful effect on the environment is an important task of EU countries and Ukraine. Ukraine is a large mineral resource base with iron ore reserves of 30 billion tons, which about 6% of world reserve. Iron ore raw materials used for the manufacture of metallurgical products are produced by mining enterprise both for domestic market and for suppliers to foreign customers. The constant increase in the cost of fuel and energy resources, the transition of carbon-neutral production, the need to increase the competitiveness of product and improvements in the environmental situation require from the side of mining enterprises wide introduce and implementation of innovative technologies at all stages of production. Today, mining enterprises of Ukraine use traction units produced by Dniprovsky electric locomotive plant. You can see it on the picture. To transform iron ore on electrified section of domestic railways. These machines were developed in 17th, 80s of the last centuries using technologies available at that time. Modernization of traction units, which are carried out by various enterprises, provide for the use of modern equipment, which positively affects their reliability and performance. The main features of the operation of traction units is quarry. Quarries are listed on the slide. 5. Collector electric motors and unregulated electric drive of auxiliary system are used on traction units. The above factors cause increased power consumption, taking into account the deterioration of rolling stock, most of which is operated with the extended service life, and the problem between traction and energy characteristic in the train task. The task of updating electric rolling stock is relevant. The authors proposed a new electric locomotive for quarry railway transport. To achieve its high efficiency, the following technical solutions are proposed. You can see it on the third slide. 4 propositions. Preliminary technical parameters, traction and braking characteristics are shown also on the slide. Here is number axis, axle load, observed. The block diagram of the electric traction drive on the electric locomotive is shown on the next slide. Here is one. The electric locomotive consists of control section and booster section. On the control section there is an input converter, which include a traction transformer and 4 QS converters. On the booster section there is onboard energy storage system, which is so popular today. They are connected to a common link to constant voltage from which a traction, asynchronous electric drive and auxiliary system of an electric locomotive are powered. This slide shows a diagram of energy flows in the traction system for such an electric locomotive. In traction mode, it's picture A. The priority is power supply from the contact network. If the total load, the tangential power and the auxiliary system exceeds a certain standard of power capacity, then the onboard storage system is connected to the load power. In simplest case, in the electrodynamic braking mode. This mode is figure B. The energy coming from the traction electric drive can be used to power the auxiliary system of the electric locomotive. It's priority usage. Charge the onboard storage system and recovery into the traction network in the case when it's in excess of the total power of the auxiliary system and the power with which the energy of storage device is charged. Thus, the problem arises of determining the parameters of the traction system of an electric locomotive and its individual components. Considering the typical scenarios of the onboard energy storage system, it's shown on this slide. The first scenario is that the power of capacity of the onboard energy storage system is sufficient to accumulate all the energy that generates during electrodynamic braking. The second scenario assumes that the power of the drive is selected from the condition of power compensation in traction mode. The power of the drive in this case is calculated by the expression number 2. To carry out calculation for both scenarios, the flowchart has been developed, which is shown here on the slide. The calculations were carried out for the railway section at example of Poltava-Gok for expo mining. The movement was carried out by the train with 14 loaded wagons. The type of wagons is 2 BC 905 from the transshipment point to the crucian factory. The best profile is shown at the figure. Here is one. For this best profile, a traction task was solved, and the result of which is determined as the depends of the tractive power, and here is the result from time. Further, this dependence was used for analysis according to the studied scenarios of the operation of the electric locomotive traction system. The calculation was carried out for the case when the voltage on the current collector is of the electric locomotive was equal 7.5 kV throughout the section. This is an artificial situation that corresponds to the worst case of the supply. Therefore, it is advisable to calculate the parameters of the traction system for such a case. Traction network current was taken as a limitation. The lower figure on the left shows the dependence of the power of the onboard energy storage system on the from current. The lower right figure shows the dependence of the working energy intensity of the onboard storage system on the current. This storage capacity is about 5,800 kW, and the minimum operation energy intensity is about 60 kW per hour. Mains current is about 600 ampere. Accordingly, in the first scenario, when the storage power is constant and sufficient to receive the braking energy, this power does not depend on the current, and the dependence of the working energy intensity has a nonlinear character. with a minimum of about 600 amperes. These differences are shown in green line. In the second case, the power of the storage is selected from the condition of compensation of power consumed from the traction network. The power of storage decreases with the increasing mains current. The operating energy intensity is also nonlinear in nature with a minimum of 700 amperes. In this case, the current power of storage should be 2800 kW and the operating energy intensity should be about 50 kW per hour. As you can see in the first scenario, the power of the onboard storage system is greater, which potentially means its higher cost. That is, capital investment will be more, which makes this option less attractive. Therefore, we consider it expedient to use onboard storage in the second scenario of operation. The power of storage is selected from the conditions that it will be compensated for the lack of energy from the contact network. Accordingly, in the modes of electrodynamic braking, energy will be both accumulated for the onboard storage and recuperated to the traction network. Thus, the priority option in the second science it requires less capital investment to create an onboard energy storage system. For a more accurate determination of the parameters of the electric locomotive traction system, it is necessary to consider the movement cycle, which includes all stages of working task of electric locomotive. For example, movement of the empty passage from the crushing factory to the transshipment point, maneuvering at the transshipment point when loading, movement of the loaded train from the transshipment point to the crushing factory, and maneuvering during unloading at the crushing factory. Thank you for attention. It was all.